Good morning, good afternoon, block 2, block 6. Here's a little bit of an introduction for you and a fair amount of detail in the upcoming slides to take you through some questions related to resonance structures, also to take you through the polarity of the molecules 1 to 13 from your molecule building activity, and kind of set up the rest of the day. So please work individually, work with a partner. You'll need your notes handouts for resonance structures, and then later on you'll need your molecule building activity stuff. So let's go. Let's get rolling. Take a break when you need to. So let's start our discussion here by drawing a Lewis structure for the nitrate ion. Nitrate is NO3 minus. I don't believe this was part of your video, so this is a nice way for us to review drawing Lewis structures. Nitrogen has 5 electrons. Oxygen has 6 electrons, and there are 3 oxygens, which is 18 electrons. So 5 plus 18 is 23 electrons. But there's a -1 charge, so I need an extra electron to make a total of 24 electrons. So nitrogen goes in the middle. I have 3 oxygens. And I'm going to have a double bond with the oxygen here. And then I'm going to have all octets for everything else. So this is 1 minus. Let's count electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I have 24 valence electrons. But why did I choose this for the double bond? Well, nitrogen looks a bit funny here because it usually only has 3 bonds in a lone pair, and oxygen maybe looks a little funny because it normally has 2 lone pairs and 2 bonds like this oxygen. So I definitely have some weirdness going on here. This extra electron causes some of that weirdness. But what if I drew the double bond here instead of here? And so it would look as a Lewis structure something like this. Or what if I drew the double bond here? And everything else would look about the same. 1 minus charge. These are 3 structures that are approximately equivalent. They just have the double bond in a different location, and these are called resonance structures. Typically with resonance structures, we draw a double-headed arrow kind of between them. If we could draw them in a line, 1, 2, 3, with a double-headed arrow in between. It doesn't matter. The key here is I have 3 resonance structures. So let's think about what that means. So let's think about bond lengths. I want you to look at your data booklet. And I want you to look at table 10 or 11. I can't remember which one. Maybe table 12. I know it's in that ballpark. We're looking for bond lengths. And what we're looking for is the nitrogen-oxygen bond length of 136 picometers and the nitrogen-oxygen double bond length of 114 picometers. I want you to find that data just to kind of verify. So this data from our data booklet makes us think that this bond should be shorter than these 2 bonds because double bonds are typically shorter than single bonds. So these are the values from the data booklet, but what does the actual data show? Not the data booklet that gives values for bonds, but what does the data show for this ion? So let's look at Adam Smith Classroom. I found the nitrate ion. I selected a nitrogen and an oxygen, and I found the bond length, 1.24 angstroms, which is 124 picometers. What about this bond length? 124 picometers. What about this bond length? 124 picometers. So the data seems to be indicating that all 3 bonds are equal length. And that means that our resonance structures are not a perfect fit for what really is happening. What is really happening is that these 3 bonds are the same. And this resonance structure doesn't show that. So we might consider drawing something called a hybrid structure. Hybrid structure is not what would typically be an answer on an IB exam, but a hybrid structure might look like this, where we have 3 oxygens, a 1- charge, and draw a dotted line to represent that there are 3 bonds, and all 3 bonds are equal. Equal length, equal strength. We can draw our lone pairs on here, and this model is not perfect because it doesn't show all the lone pairs, but it does show that these 3 bonds are all the same. That's the data. So we have 3 resonance structures. That's an imperfect model when the data actually shows us that it's a kind of a hybrid of the 3 resonance structures, kind of an average. So the data shows that it's 124 picometers, which is kind of in between a single bond and a double bond. It's between the length of a single bond and a double bond. So that leaves me with something to describe called bond order. And then I'll talk about these diagrams on the left. When I look at these 3 resonance structures, I'm going to draw them in simplified form. Let's see, single bond, double bond. We're going to look at this bond. If I look at that bond, I have a double bond plus a single bond plus a single bond, and I have 3 structures. I have 3 resonance structures, 1, 2, 3. So a double bond counts for 2, a single bond counts for 1, and a single bond counts for 1 in 3 structures. That gives me a bond order of 1.33, or 4/3. Notice that this 1.33 is kind of greater than a single bond, but not as much as a double bond looking at this table here. So what we're learning is that this structure, which shows kind of a localized double bond, is not accurate. We actually have a hybrid where these electrons are delocalized. We will learn a lot more about delocalized electrons next week when we study hybridization. So this is just a bit of an introduction to resonance structures and the idea of a hybrid structure. This is another diagram of the nitrate ion, and it's a little bit maybe hard to understand. We have some p orbitals here, and these red lines indicate delocalized electrons being shared. I'm not going to go into a lot more detail because we will learn more after we learn about hybridization. This structure will make more sense. So this is kind of a preview. Let's look at benzene. Benzene is C6H6. So I have 6 carbons, and each of these carbons has a hydrogen, and they're just not drawn, but I could draw the hydrogens here. This is a line structure. So I have a hydrogen on every carbon. So I could draw 2 resonance structures. The double bonds here, here, and here, or the double bonds here, here, and here. Those are my resonance structures. I want you to go back to the bond lengths section of your data booklet and see if you can find carbon-carbon single bond, carbon-carbon double bond, and the carbon-carbon, I'm not sure what the notation will look like. It might look like this for benzene. I want you to find that data. So the data tells us that a carbon-carbon single bond is 154 picometers. It tells us that a carbon-carbon double bond is 134 picometers. And it tells us that benzene is 140 picometers. Notice that 140 is somewhere approximately in the middle of 134 and 154. So let's think about bond order. Let's take this bond right here. It's a single bond here. It's a double bond here, and there are 2 resonance structures. That's 3 halves, or a bond order of 1.5. So these bonds in benzene are shorter, sorry about that. They are shorter, 140 picometers, shorter than a single bond, but longer than a double bond. because they're about a bond and a half. The resonance structure might look something like this, where I have delocalized electrons. And we'll learn more about what that means when we study hybridization. Here's benzene. We might draw it with a circle to indicate these delocalized electrons here. These electrons are localized, so if there's a double bond here, a double bond here, and a double bond here, those are localized electrons. But it turns out that the electrons can be delocalized, which provides a lot of stability. So that means we have benzene as a hybrid structure, and when these are the two resonance structures of benzene. This is another look at it. Each of the carbon atoms in benzene has an unhybridized p orbital. What does that mean? We'll learn more about it next week, and we will study benzene with more detail, I promise. So there are pi electrons that spend time in all of these orbitals approximately equally instead of being localized in one spot. And as I mentioned, after we learn more about hybridization, we'll understand resonance even more. It's kind of that, there's so much information, you can't get it all at once, so you have to pile it together and really keep relating it to what you already know. So I hope that was a little bit helpful to increase your understanding of resonance, even if it's not perfect yet, and that's okay. Now, please find your molecule building activity handouts. And you might consider taking a break right now. If you've been sitting for a while and you want a little bit of a break, take a little bit of a break. I want you to confirm your work on everything except hybridization, and I want you to confirm your VSEPR handout. Oops, I don't know how to spell VSEPR. Sorry. I want you to work on confirming your VSEPR handout and the 13 molecules. So, let's look at them. Molecule number 1, beryllium dichloride. Beryllium dichloride is nonpolar. Each of these bonds would be a polar bond, but because the bonds that are polar are in exactly opposite direction, the polarity cancels, and we have an overall polarity of nonpolar. Hybridization we're going to not worry about yet. Remember, we'll come back to that next week. So what I'd like you to do now is pause the video. Please pause the video and look through molecules 2 to 13 to determine their overall polarity. Once you've done that, come back and push play. Check your work. Pause the video. I want you to do some thinking before you just get my answers. Alright, welcome back. Before you pause the video, this is BF3. It is nonpolar, even though these bonds are polar, because they are evenly distributed 120 degrees apart. This is a nonpolar molecule. SO2 is a polar molecule. Sulfur would have a partial positive charge, and the oxygens would have a partial negative charge. Oxygen has a higher electronegativity. The atom that has a higher electronegativity is able to attract these bonded electrons more tightly, and so we get these partial positive charges. Partial negative charges on the oxygen, partial positive charge on the sulfur. CH4 overall nonpolar because these 4 bonds are all 109.5 degrees apart. And the bonds are really not all that polar to begin with. The difference in electronegativity is not that great. Ammonia, trigonopyramidal. That means these angles are about 107, and because there are only 3 atoms bonded to the nitrogen, this is no longer an equally distributed arrangement, and so NH3 is polar. Water. I tend to prefer this Lewis structure because it shows water as a bent molecule, which is correct. This Lewis structure is just that shows the bonding, that there are 2 hydrogens bonded to the central oxygen. Bond angle is 104.5 though. 104.5 is the angle, and that makes water polar because oxygen is about 3.6 on the electronegativity scale. Hydrogen is 2.2, that's a difference of 1.4. And because water is bent, the overall polarity is towards the oxygen. So we would draw an overall dipole towards the oxygen, with the hydrogens having a slightly positive partial charge and the oxygen with a partial negative charge. PCl5, non-polar because everything is distributed equally. This is the axis. Everything on the axis is going to be evenly canceled. And then these three atoms are on the equator. Everything there would cancel equally, and so I end up with overall non-polar. SF4 would be polar. It's not symmetrical anymore, and these angles are actually going to be less than 90 degrees. So that means that these atoms are pushed a little bit closer together. There's no fluorine on this part of the molecule to spread it out evenly. So we have a polar molecule with the fluorines having a partial negative charge and the sulfur having a partial positive charge. This is ClF3. This is also a polar molecule. Fluorine has a higher electronegativity, so that's where the partial negative charge would reside, and the chlorine would be partial positive charge. This is I3 minus. Forgive me here, this is just supposed to be with one minus sign, not three minuses. I apologize about that. My mistake. Now I've got lone pairs around the center atom. I have lone pairs on the iodines as well if you want to look at those. The key here is that these lone pairs are evenly distributed around here, and so these bond angles will be 180 degrees, which means this is a non-polar molecule. Or we might say not applicable since it's an ion. I think either one would be appropriate for us to think about. SF6, non-polar. Everything is evenly distributed. All of the angles are 90 degrees. Not 90 degrees C, sorry, just 90 degrees. IF5, polar. The atoms are no longer arranged evenly around the center iodine atom. And so, because of that, the polarity would be towards the fluorines. The fluorines are going to have a slight negative charge. The iodine is going to have a slightly positive charge. And the last molecule is XeF4. This is also non-polar because all of the bond angles are going to be 90 degrees. So the polar bonds would distribute themselves evenly to make a non-polar molecule. And that is all 13 molecules. We will do more when we study resonance structures. Just so you know, we'll have a little bit more practice on this next week after we learn about hybridization and resonance structures. So, at this point, you can ask the sub for the handouts for the naming practice and practice problems 4.2. I want you to work on a HAL self-assessment. I'm supposed to be entering a HAL grade for you. So I'm interested in learning what you think about your HAL, and so please just complete another page on your HAL Google Doc. In terms of the naming practice, when you are in class on Friday, you will be receiving a formative quiz on names and formulas. And by formative here, I mean not for a grade. You are just going to kind of get a feel for where you are on names and formulas. And so there are a couple practice handouts. Mark schemes are posted in the Google Drive folder for topic 4. There also are some IB style practice problems for you related to covalent bonding. In terms of homework note video tonight, finish any work you need. You'll probably have a little bit of time next block if you don't finish all of these practice problems. Just remember next block there'll be a formative quiz. And the substitute is going to return paper 1 to you, and I'm going to ask for your flexibility and patience regarding paper 2. You know that I was absent on Monday due to illness in the family. It means I had almost no time this weekend to do any work. And so I'm a little behind on my marking. And I would hope that you understand that I gave a large amount of flexibility last week when I had 20 students in my 5 classes ask me to take the assessments at a different date due to exchanges and conflicts. So because I'm willing to be so flexible, I'm asking you to be a little bit flexible now as well. But I do appreciate your work, and I look forward to seeing you next week when I get back. Thank you. Have a good day.